This is the second of two videos outlining the solutions to flow problems at the end of the flow unit. Here we are solving problems 16 to 21, beginning on page 133. And note that detailed, complete type solutions to all the flow problems are posted on Blackboard. Question number 16. If the head loss between sections 1 and 2 is 3.5 feet of the fluid, calculate the pressure in PSI gauge in the 3-inch section of pipe, that's up here. The velocity in the 6-inch pipe is 10 feet per second. So we're asked to calculate the pressure here. Looks pretty straightforward. We'll use Bernoulli's equation and put the terms in. I have it here. So Bernoulli's equation is the pressure at point 1 plus the elevation at point 1 plus the kinetic energy at point 1 is equal to the pressure at point 2 plus the elevation at point 2 plus kinetic energy at point 2. And we are given a head loss due to friction. We're given 3.5 feet. We're not involving a pump term, so that's not here. The elevation at the lowest point is always set to 0. The higher elevation is 18 feet. We're given velocity 1 is 10 feet per second. We can calculate V2 as V1 times the ratio of diameter squared. That'll give us that term. So it remains to find the pressure at point 1, so we can find the pressure at point 2. We're given that as 28 psi gauge. We have to enter this in this form of Bernoulli's equation as a height of the liquid. This liquid is water. So we'll say it's 28 psi gauge, and there are 33.9 feet of water for every 14.7 psi. You'll get a height of water. Substitute here and rearrange and solve for H2. And that'll be it. Problem 17. A pump takes water at 50 degrees Fahrenheit from a large reservoir. Here's the reservoir. And delivers it to the bottom of an open elevated tank. Here's our open elevated tank. Notice it's open. We're seeing atmospheric pressure is acting on it. The level in the tank up here averages 160 feet above the level in the surface of the reservoir. Now, there's a 3-inch standard pipe. We have a head loss of 18.6 feet. The pump delivers 150 imperial gallons per minute and has efficiency of 55%. What horsepower is consumed by the pump? So you appreciate that we can calculate the amount of pressure the pump has to deliver to do this work, but then we're going to have to divide that by 0.55 to determine how much horsepower is actually consumed. We have to figure out the pressure of the pump that it's going to do this work. Let's try that. Alright, so I filled this in a bit. So again, we're trying to calculate the amount of power consumed. It'll be the amount of power produced divided by 0.55. You always consume more than you actually produce. How do we get power? Power is P times Q. Right? So Q is just the flow rate. It's given as 150 imperial gallons per minute, and you can convert that to cubic feet per second. Where do we get this pressure term from? Well, the pressure term will have to come from Bernoulli's equation. Let's figure out what pressure is involved in doing this. And we'll need that pressure in pounds per square feet to combine with cubic feet per second to give us power in foot-pounds per second, which we divide by 550 to get horsepower, and then divide by 0.55 to get the power consumed. But let's go back to Bernoulli's equation. We have a pump, so there's a pump term here, plus the pressure in the system at point 1, plus the elevation at point 1, plus the kinetic energy term at point 1 is equal to the pressure in the system at point 2 at the bottom of the elevated tank, plus the elevational potential energy. How far is it lifted it? It's lifted it this far, plus the velocity term and we are given that the head loss due to friction is 18.6 feet. So what do we do with this? Well, what is the amount of pressure acting at point 1? Would you agree with me that it is 0? It's only atmospheric pressure, and it's acting on both surfaces, so that's not going to lift the fluid at all. We can't get any help from the pressure of the atmosphere here. The lowest elevation is always set to 0. Now what about the velocity? It's kind of almost misleading here. They're telling us it's a 3-inch standard pipe. We're given a flow rate. You might think, well, we could calculate the velocity in this pipe, and yes, we could, but that's not the point. The point is, what's the velocity at the starting point, and that would be essentially 0. It's starting from 0. It doesn't have any velocity to begin with. In a large reservoir, the velocity is 0. So we're getting rid of a lot of our terms here. Okay, what about velocity 2, way over here? What's the velocity of the fluid in this large tank? It's going to be essentially 0, right? Because, well, it's such a large reservoir, it's negligible. We do have the head loss due to friction, so all we need then is the pressure at point 2, which is the amount of fluid pushing down at this point, and its elevation at point 2. We're not given those values, but we are given the sum of those two values, right? The sum of the elevation plus the pressure pushing down is 160 feet. Just for argument's sake, let's say that this elevation was 80 feet and we had 80 feet of water pushing down, then the sum of H plus C is 160. We're told it's 160, so that's not as bad as it might seem. 160 feet is the sum of the pressure and elevational potential energy. So all we have here is 160 plus 18.6. We'll have 178.6 feet of water, which you can convert to pounds per square foot, and so on. Question 18. At a point A in a pipeline carrying oil with a specific gravity of 0.9, the diameter is 6 inches, and the pressure is 25 psi gauge. At another point, B, which is 20 feet higher than A, the diameter is 12 inches and the pressure is 18 psi gauge. If oil flows in the system at a rate of 1 cubic foot per second, is the oil flowing from A to B or B to A? That's an interesting question. Now when you just look at that, you think, well, the pressure is greater at A than B, so shouldn't it flow from high pressure to low pressure? Yes, but you really need to consider the total mechanical energy, right? Just climbing the hill will reduce the pressure. So you need to consider the total pressure at A and compare it to the total pressure at B, and the fluid will flow from the point of highest total mechanical energy to the point of lesser total mechanical energy. We'll have to use Bernoulli's equation to work this out and compare the total mechanical energy at the 2 points, point A and B. So I've written out Bernoulli's equation. I put the left half for point A versus the right half for position B. Now, the elevation at point A we know will be 0 because that's the lower one, and the elevation at point B will be 20 feet because it's 20 feet higher. For the velocities, we're given a flow rate as 1 cubic foot per second, so we could calculate a velocity using the areas from the diameters. So for example, at position A, or D1, the diameter is 6 inches. Convert that to feet. You'll get the area in square feet divided into the flow rate in cubic feet per second, and you'll get feet per second for velocity 1, which you can put into this kinetic energy term. For V2, it's simply V1 times the ratio of diameter squared, and you can put it in for this velocity term. So we'll have everything except our pressures H1 and H2. Now be careful, these have to be in height of the working fluid in the system. These have to be height of oil, not height of water, not psi, height of the working fluid. So we have to convert these pressures to height of oil. So we're told that the pressure at point 1 or point A is 25 psi. Let's convert that to height of water. 33.9 feet of water for every 14 psi. So 25 psi is equivalent to 57.7 feet of water. How much oil would that be? Well, the oil is lighter. Most oils are, right? So we need a taller column of oil to exert the same pressure as 57.7 feet of water. So divide by 0.9 and you'll have 64.1 feet is the height of the oil. I worked out the first one for you. You can work out the second one yourself. So this term here, pressure 1, is 64.1 feet of oil, and you'll get 1 here similarly for H2. Now, just to help you with the wrap-up, I went ahead and calculated the total mechanical energy at A, including elevation and pressure and velocity, is 64.5 feet of oil, versus the total mechanical energy at point B is 66.1. So in fact, the total mechanical energy at B is greater than A, and so the flow would go from B to A. So it goes from lower pressure to higher pressure, because we have to consider all forms of energy. Interesting. Problem number 19. An aqueous methanol solution with a specific gravity of 0.83 and an absolute viscosity of 0.96 centipoise is to be pumped from a storage tank to a process through a 1¼ inch standard steel pipe. The process end of the line must have a pressure of 8 psi gauge, and it is 22 feet above the surface of the liquid in the storage tank. The flow is rated at 20 imperial gallons per minute, but may be overloaded by 50%. The head loss due to friction is 300 feet of methanol. Assuming a 60% pump efficiency, calculate the power consumed by the electric motor for this service. Report your answer to 3 sig figs. So we're asked to calculate this term, and the power consumed, which is the power input. And that'll be the power output of the pump divided by its efficiency as a decimal. So if you don't do anything else, make sure you divide by 0.6 and get a mark for that. And so how do we get this power output? Well, we're going to calculate it from pressure times flow. The flow rate was listed as 20 imperial gallons per minute, but we have to overload it by 50%, so I multiply by 1.5. That would be 30 imperial gallons per minute. We'll have to convert units, and the pressure would have to be obtained from Bernoulli's equation, because we have quite a dynamic system here. This will be the pressure of the pump here, what we need to solve for. So let's give that a try. So I've written it out here. I just want to remind you that a 1¼ inch standard pipe means it's a schedule 40, and you have to look up the actual dimensions and calculate it. You can't assume it's exactly 1.25 inches. All right, so again, we're going to plan for 30 gallons per minute, convert it to cubic feet per second. We'll need to get the pressure of the pump, which will have to be in pounds per square feet. In our Bernoulli's calculation, we'll be calculating the height of the fluid, which happens to be methanol. We'll have to convert that to feet of water, and then from feet of water to pounds per square feet. Then that pressure times the flow rate in cubic feet per second will give us power in foot-pounds per second. We convert that to horsepower by dividing by 550. Divide by 0.6 to find the power consumed. So what remains to be done is to calculate this pressure supplied by the pump. So the first term here is the hydrostatic head at the intake of the pump, which would be like right here. So what's the pressure at this point? Well, it's the height of the liquid, which they didn't give us, so I just called it x feet of methanol. Now the elevation, of course, will be 0 feet. Now the velocity term, what would be the velocity at the intake of the pump? So this is coming from a large tank like a reservoir. It'll essentially be 0. So that kinetic energy term is kindly 0. Let's move to the end here. We're told that we have 300 feet of head loss due to friction in the methanol. That's good, that's given. Now, the velocity, we'll need to get the velocity term because it is moving through this section of pipe. It started at 0 and now it's moving into the process. So we can't ignore that. We know that velocity is Q over A. Again, we have our flow rate of 30 imperial gallons per minute as cubic feet per second. We'll divide by the area in square feet. So the area is pi d squared over 4. We need that in feet, but we've got to work all the way back from our 1 1/4 inch schedule 40 steel pipe. We go to the pipe tables and find that the internal diameter is the outside diameter minus 2 wall thicknesses. And I worked this one out for you. 1.660 is the outside diameter, minus 2 wall thicknesses is 1.38 inches is the internal diameter. You convert that to feet, then get the area, which will be square feet, divided into the flow rate in cubic feet, and you'll have a velocity term in feet per second, which you're going to put in here and calculate the kinetic energy term. Let's do this pressure term here first. The pressure at point 2, which is right up here, what would that be? Well, in this case, we don't have a height of water sitting above it. We're told that it's 8 psi gauge. That's how much pressure it's going to be working against. So we'll have to convert that to a height of methanol solution because we're working with methanol. So we take our 8 psi gauge, convert it to a height of water. There's 33.9 feet of water for every 14.7 psi. Then convert that to a height of methanol that gives the equivalent pressure. And of course, methanol being less dense than water would require a higher height or column of methanol. So make sure you divide by the specific gravity, 0.83, to make that larger. And it's 22.2 feet of methanol. That pressure is equivalent to 8 psi gauge. And that'll go in here for the term H2. And that just leaves us with the elevation term. So we're pumping methanol from the bottom all the way to the top. And that's 22 feet plus X. We were never given X, but you notice we had X feet for the hydrostatic head at 0.1, so nicely that will cancel. So we'll wind up with 22.2 feet of pressure plus 22 feet of elevation plus 300 feet of hydrostatic head plus a small term for the velocity. You sum all those up and you'll find out the pressure that must be developed by the pump. That will be feet of methanol. You want to convert that to feet of water. It will be slightly lower height of water. Convert that to pounds per square feet, and that's it. So a little tedious, but with practice, they get better. Practice always makes better. Problem number 20. We have a standard 2-inch steel pipe, and standard means schedule 40. It's conveying oil of specific gravity 0.85 at a rate of 90 liters per minute. At a certain point in the line, the pressure is 310 kilopascals. Calculate the Reynolds number, and the pressure at a point in the line that is 61 meters further along in the direction of flow and 15 meters lower in direction. Assume a head loss due to friction of 1 meter of oil, and we're told the oil has a viscosity of 20 centipoise at the temperature of the process. So we're actually asked to calculate two things, Reynolds number and also the pressure at point 2 in the process. So let's tackle that one. So I started by calculating the diameter because we're going to need it for our Reynolds number as well as our Bernoulli's equation. So we're told we have a 2-inch schedule 40 steel pipe, and again I worked this one out for you. The internal diameter is the outside diameter minus 2 wall thicknesses, and that's 2.067 inches. In the SI system in which we're working here, we'll need it in meters. So there's 1 inch is 2.54 centimeters or 0.0254 meters because there's 100 centimeters in a meter. So I convert from inches to meters, and that's 0.0525 meters. Then we need the velocity of the fluid. We'll need that for Reynolds number calculation for sure. V is Q over A. We're told that the flow rate is 90 liters per minute. You'll want to convert that to cubic meters per second. For the cross-sectional area, well, we have the diameter, so we'll use pi d squared over 4. We calculated that was 0.0525 meters over there, and work that out. We'll get square meters divided into cubic meters per second will give us a velocity in meters per second. For Bernoulli's equation, the pressure at point 1 plus the elevation at point 1 plus its velocity term at point 1 equals the pressure at point 2, which we're asked to solve for, plus the elevation at point 2 plus the kinetic energy term at point 2 plus the head loss due to friction, left side equals right side. We're told that the pressure at point 1 is 310 kilopascals. We're going to use that in Bernoulli's equation, but we have to convert it to height of the fluid that we're using, and that's height of oil. We want that in meters of oil. So first we'll convert that to meters of water using atmospheric pressure. There's 10.33 meters of water for every 101.3 kilopascals. That'll give us the meters of water, but then we need to convert that to meters of oil. And since the oil is less dense than water, the oil column must be higher, so make sure you divide by the specific gravity of 0.85, and that gives you the height of the oil. And that'll be this first term in Bernoulli's equation. Now the elevation at point 1 is 15 meters higher than point 2, so that's 15 meters. What about the velocity? We're going to actually calculate it up here for the Reynolds number calculation, but we don't really need it here because notice the pipe is not changing diameter. So whatever velocity 1 is, it's the same as velocity 2. So whatever that number is, it'll cancel, so you can ignore it. We're going to solve for H2. Elevation 2 is 0. And we're given that the head loss due to friction is 1 meter. So if you collect all these terms and solve for H2, you'll find it's 51.1 meters of oil. And I want to take you through the process of bringing it back to kilopascal, so I gave you the value here. Convert that height of oil to a height of water. Recall that the height of water would be less than the height of oil because water is more dense. So make sure you multiply by 0.85 this time rather than divide to get a smaller column of liquid. It would be less water. 43.4 meters of water. You can convert that into kilopascal, and that's 426. So that's the first part of the problem solved. The second part asks us for the Reynolds number. So recall the Reynolds number. You'll be given the equation is the diameter of the fluid, which is the internal diameter of the pipe, times the velocity of the fluid, times its mass density, divided by the absolute viscosity. And I'm working here in the SI system. We already calculated the internal diameter of the pipe, which is the diameter of the fluid. The velocity, I didn't calculate the number, but I showed you the setup for it. We just have two more terms here. So we need the mass density of the fluid in the SI system. Recall the specific gravity of the oil is 0.85, which means its density is 0.85 grams per milliliter. And so in the SI system, that would be 850 kilograms per cubic meter. We also need the absolute viscosity in the SI system. We're given 20 centipoise. Kind of unfamiliar turf to us. Take a look at the flow notes. Here we're told that the SI unit for viscosity is Pascal seconds, which is a kilogram per meter second. And we have a conversion factor from centipoise to Pascal seconds. So we have a value of 20 centipoise. If we divide by 1,000, that should give us the viscosity unit in the SI system. So here I have 20 centipoise divided by 1,000 centipoise per Pascal second gives me 0.020 Pascal seconds, or 0.020 kilograms per meter second. And from that you'll work out the Reynolds number and determine whether the flow is turbulent or laminar or transitional. And you'll notice that all the units cancel. And that's a condition for Reynolds number, is that there are no units to it. It's dimensionless. Last problem, problem 21. A technologist is investigating a gravity feed that is to supply a vinegar solution to a processing unit as shown in the diagram. The process requires a flow rate of 10 imperial gallons per minute and a pressure of 10 psi gauge at B down here, just before the processing unit. Vinegar has a specific gravity of 1005, has a viscosity of 1 centipoise. The piping is 3-inch schedule 40 steel pipe. Calculate the velocity and the Reynolds number at point B. Assume the frictional head loss is 0.11 feet of fluid. Determine the minimum height of vinegar required in the storage tank to feed the process as required. So we have two things to calculate. We have Reynolds number, and we have the elevation, that would be elevation 1, the height of liquid in the storage tank. We see here that the storage tank, the bottom of the tank is 20 feet above elevation B, and so elevation A would be above that. At some point there'll be enough liquid in this tank to feed the process. How many feet would that be? We'll calculate the total elevation right up to point A, and we'll subtract from that a 20 feet elevation at the bottom of the tank and figure out how many feet must be in the tank. At least that's the plan. Alright, so let's solve this one. So we're going to need the diameter of the pipe. We're told it's schedule 40, and I didn't work it out for you, but you can do that. From the diameter you can calculate the cross-sectional area, pi d squared over 4, and make sure you're working in square feet. Then we'll need the velocity, and the velocity is Q over A. We are given the flow rate as 10 imperial gallons per minute. Convert that to cubic feet per second. You'll have the area from up here, and that'll be square feet. So cubic feet per second divided by square feet is feet per second for the velocity. That'll be the velocity moving through the pipe, and the pipe doesn't change size, so that'll be the velocity at point B, where we have to calculate the Reynolds number. Okay, so we need the pressure at point B. It's given as 10 psi gauge. We need that in height of a liquid to put in Bernoulli's equation. This is going to be Bernoulli's equation. We'll have the pressure at point 1, which I'm calling point A, and there's no pressure there, right? There's only atmospheric pressure, and so we'll ignore that, and we want to determine how much fluid pressure is required to drive the process. So let's ignore atmospheric. For all we know, atmospheric pressure is acting in the processing unit. We're not told, so we'll just ignore atmospheric pressure. And Z1 will be the elevation at point 1, which we're trying to solve for. What about velocity term? Well, that's going to be 0 because there's no velocity at the surface of a large tank. It's not moving. There's a velocity in the pipe at point B, and we'll cater for that later. That'll be equal to the pressure at point B, which we're going to work out in just a moment. And then the elevation at point B is going to be 0. And then we'll have a velocity term that was calculated up here. So the velocity in the 3-inch schedule 40 pipe was calculated from the flow rate divided by the area of the pipe, and so that gave us the velocity term, which we'll place down here. And the head loss due to friction was given as a small quantity, 0.11 feet of vinegar. The only question is, how do we figure out the pressure at point B as a height of vinegar? So we'll take 10 psi gauge, that's pressure at point B. Let's make that a height of water using atmospheric pressure, and that's 23.1 feet of water. Now the vinegar is just slightly more dense than water, which means that you need slightly less height of a column. So I'm dividing by the specific gravity of vinegar, 1005, so it's a very small difference. It becomes 23.0 feet of vinegar instead of 23.1. And that will be the pressure at point B in the unit. I think that's all we need. So when you collect these terms, 23 feet is the pressure at B, plus the 0.11 pressure loss due to head loss due to friction, comes out that Z1, this height right up here, must be 23.1 feet of vinegar. And since the tank, The bottom of the tank is 20 feet high. That means that we need to keep at least 3.1 feet of vinegar in the tank to supply the pressure and the velocity required in the system. So presumably you would put in a floats mechanism in the tank that will control the level in the tank if they want to keep it not greater than 10 psi gauge and not greater velocity than that. Interesting problem, actually quite practical. Okay, so how about the Reynolds number? Well, the Reynolds number is the pipe diameter, which you will have calculated, times the velocity, which you will have calculated, times the mass density. So what is that? Well, we're told the specific gravity of vinegar is 1005, which means the density would be 1005 times that of the density of water. The density of water in the British system is 1.9403 slugs per cubic foot. So if you multiply that by 1005, it's just 1.950 slugs per cubic foot. And that'll be the density term you use in this calculation. We're given the absolute viscosity is 1 centipoise. We need to convert that to the British units. So if you go to your flow notes, you'll see here that 1 centipoise is equivalent to 2.089 times 10 to the minus 5 slugs per foot second. So we can put that value right in. Is equivalent to 2.089 times 10 to the minus 5 slugs per foot second. Per centipoise, that'll be our value. When you evaluate that, you'll find the Reynolds number is 12,400, and that is turbulent flow. And again, notice if you include all the units together, they cancel, and Reynolds number is in fact dimensionless. Now that is the end of the problems for the flow unit. So you can see that these will require a little more practice than some of the other problems in the course. So give it some time. It will come. Just follow your units and give it your best. Thanks for listening.